Humanity no longer wants to stop at simply setting foot on the moon to collect soil samples as in the Apollo era. The current objective is to build settlement infrastructure that allows humans to survive there for years, rather than carrying out isolated missions. NASA and private corporations are redefining the lunar surface as a fuel transfer station and logistical hub for the goal of reaching Mars. The real challenge lies in creating a closed ecological system capable of sustaining life across multiple generations under extreme physical constraints. NASA must eliminate its dependence on supplies transported from Earth. But how can the first city be established on a surface covered in highly adhesive dust and exposed to extreme radiation? Instead of the flat equatorial plains where the Apollo missions once landed, the lunar South Pole has been selected as a strategic location due to its distinct geological characteristics and unique illumination geometry. Here, because the moon's axial tilt is nearly perpendicular to the plane of the ecliptic, sunlight constantly skims along the horizon, creating deep impact craters with regions of permanent shadow. Because there is no atmosphere to scatter and retain heat, temperatures within these shadowed regions remain extremely low, turning them into cold traps capable of capturing and preserving volatile molecules from billions of years ago. Data from the Lunar Reconnaissance Orbiter and Chandrayaan-3 have confirmed the presence of hydrogen and water ice embedded within the rocky soil layers in these polar regions. The existence of water in its solid state does not merely serve the biological needs of astronauts, but also functions as a core chemical resource for space infrastructure. Through the process of electrolysis, water is separated into oxygen to sustain respiration and liquid hydrogen to serve as rocket propellant. The ability to produce fuel on-site transforms the lunar South Pole into a strategic resource supply station, allowing a significant reduction in the amount of cargo that must be transported out of Earth's deep gravity well. In the future space economy model, these locations effectively become the oil fields that power all interplanetary transportation activities. To operationalize this extraction capability, the Viper rover is being developed with the mission of directly drilling into the surface to map the distribution and concentration of water resources. The measurement data collected by this vehicle will determine the locations where habitation modules are established, since the distance to resource deposits is directly proportional to the efficiency of maintaining logistical systems. However, the value of these resources is inversely proportional to the ease of technical operations. The ice-bearing regions are located within hazardous terrain filled with steep cliffs, creating major risks for the landing and mobility of robotic systems. The greatest paradox lies in the conditions of illumination and communication. Sunlight at the lunar South Pole always remains at a low angle, creating long shadows with extreme contrast. This disrupts optical sensors and navigation camera systems, which were not designed to operate in environments with such severe differences in lighting intensity. At the same time, maintaining direct communication with Earth is obstructed by the high mountain ranges surrounding the craters, requiring relay stations or intermediary satellites to ensure that data transmission remains uninterrupted. In addition, the temperature differences between continuously illuminated regions and permanently shadowed areas generate thermal stress on structural materials. Mechanical components become prone to brittleness and fracture. Lubricants solidify, and electronic systems face the risk of performance degradation in the extreme cold environment. This physical mechanism forces engineers to prioritize active thermal protection solutions rather than relying on conventional passive structures. However, even if the challenges posed by the lunar South Pole's terrain and lighting conditions are resolved, humanity's long-term settlement efforts will still face a variable capable of disabling entire mechanical systems: regolith, dust. This layer of dust is not merely loose soil and rock like that found on Earth, but the product of billions of years of meteorite impacts pulverizing the lunar surface in a vacuum environment. In the absence of natural erosion, agents such as wind and water to smooth their edges, These dust particles retain extremely sharp geometric structures, similar to microscopic shards of broken glass. Under the direct influence of solar radiation, this dust becomes electrostatically charged, resulting in an extremely strong adhesion capability to virtually every material surface, from metal and glass to the complex woven fabrics of astronaut suits. Removing the dust through conventional mechanical methods becomes nearly impossible, creating a continuous and difficult-to-control risk of system contamination. Real-world data from the Apollo missions confirmed the destructive nature of regolith on engineered systems. The sharp edges of the dust act like a powerful industrial abrasive, rapidly wearing down mechanical joints, damaging the airtight seals of spacecraft, and causing severe scratching on observation lenses. When it accumulates on thermal control systems, the dust alters the surface albedo, increasing the absorption of thermal radiation and leading to overheating in sensitive electronic equipment. If astronauts inhale these fine dust particles with their sharp-edged structures, they can cause mechanical damage to lung tissue and eye irritation, similar to the effects of silica dust or fiberglass, directly threatening the crew's ability to maintain their health within the closed environment of a habitat. The vacuum environment, combined with gravity only 1/6 that of Earth, further intensifies the mechanical risks posed by the dust. When a spacecraft lands, the exhaust plume from its engines blows away the loose, unconsolidated regolith, turning it into high-velocity projectiles traveling along ballistic trajectories. Because there is no atmospheric drag, these dust particles do not settle immediately but can travel hundreds of meters or even several kilometers, causing damage to power stations, solar panels, and habitat modules that had been established beforehand. Humanity cannot sustain a long-term presence by relying solely on natural surfaces. The accumulation of dust on solar panels will reduce the efficiency of photovoltaic energy conversion, while the infiltration of dust into air filtration systems will cripple the ability to regenerate oxygen. The direct consequence is that permanent landing pads, transportation routes, and ground stabilization solutions must be implemented from the very beginning. The contradiction between the ultra-fine size of the dust and the sensitivity of life support systems forces engineers to treat regolith management as a top priority before considering more complex architectural structures. The construction of permanent infrastructure is not solely intended to support transportation. Its fundamental purpose is to create a barrier that prevents this mechanical enemy from destroying the very foundation of the entire city. Once regolith dust has been identified as the greatest technical obstacle to long-term survival, controlling it can no longer rely solely on passive containment measures. Instead, it requires a fundamental physical and mechanical transformation that turns this hazardous material itself into a foundational construction resource through in-situ processing methods. In the initial stages, short-term solutions focus on using polymer-based ground stabilization compounds to compact the surfaces of landing pads and transportation routes. However, the payload limitations of launch vehicles make it impractical to transport large quantities of chemicals or construction materials from Earth on the scale required for an entire city. Every sustainable settlement model must be based on the principle of utilizing local resources, with regolith becoming the primary raw material for production. One of the physical mechanisms currently being tested by the European Space Agency is the laser sintering process. By using high-energy beams to locally melt lunar dust particles, the loose powder layer is transformed into a vitrified state, creating solid surfaces capable of bearing loads and resisting abrasion. Another energy optimization approach involves the use of giant Fresnel lenses to concentrate sunlight directly onto the surface. This focused thermal energy is sufficient to melt regolith without the need for complex electrical power conversion systems, allowing autonomous robots to create networks of roads and landing pads by melting the very ground they travel across. Alongside surface stabilization efforts, 3D printing technology is reshaping the way protective structures are constructed. NASA and companies such as Icon are developing large-scale 3D printing systems that use regolith mixtures combined with specialized binding agents or fully melted regolith to build habitation modules layer by layer. Lunar bricks produced through the compression and thermal processing of regolith are also being tested, including aboard the Tiangong space station, in order to evaluate their durability in high radiation environments. The transition from inflatable structures transported from Earth to buildings constructed from local stone and glass significantly increases the thickness of the protective shell, enabling more effective shielding against micrometeorites and cosmic radiation. The success of ISRU technology on the Moon establishes a mechanical precedent for all future deep space missions. If humanity cannot achieve self-sufficiency in construction materials derived from the surrounding environment, the expansion of any base will always remain constrained by the costly supply chain from the home planet. Transforming dust into bricks and soil into glass represents the transition from a state of dependent exploration to one of industrialization in space, creating the essential foundation required to realize settlement models on Mars. The next practical question is how humans can sustain their existence and maintain operational functionality within an environment where every direct interaction with the outside world carries a high level of risk. Unlike the International Space Station, ISS, where astronauts live inside a floating and completely sealed structure, a lunar city requires a far more complex survival model that combines the stability of stationary habitation bases with the mobility of flexible pressurized systems. The regular use of extravehicular activity suits for walking on the surface is not feasible. The barrier is not limited to oxygen consumption or the lengthy pressure adjustment procedures, but also includes material degradation caused by the abrasive effects of regolith dust. To overcome this challenge, the city must operate as a closed ecosystem in which humans can move between different sectors without being exposed to the vacuum environment. The Lunar Cruiser project, developed by JAXA and Toyota, is an example of an extraterrestrial mobile habitat solution. This vehicle is designed with a pressurized cabin that allows astronauts to live, work, and travel across long distances for weeks without needing to wear protective suits. The introduction of these vehicles transforms operational workflows into a seamless continuum, extending from habitation zones to autonomous vehicles, through laboratories, and ultimately to resource extraction sites. Every node within this network is standardized in terms of pressure and atmospheric composition to ensure safety. Movement within sealed environments is not only intended to protect equipment, but also to minimize the amount of time astronauts must be exposed to the hazards of the external environment, thereby optimizing work efficiency during extended operational shifts. NASA's Foundation Surface Habitat serves as the central hub of this network. It is not merely a shelter, but an integrated system that combines the functions of a miniature hospital, a biological research center, and a technical operations coordination station. Here, astronauts not only carry out specialized missions, but their own bodies become subjects of continuous observation. The transition from a cramped landing craft to a multifunctional architectural structure reflects the objective of building a miniature society capable of self-repair and maintaining human health against the effects of the extraterrestrial environment. However, the low-gravity environment reduces the mechanical load placed on the skeletal system, leading to rapid bone mineral loss and severe muscle atrophy if mandatory exercise regimens are not maintained. In addition, high-energy cosmic radiation continuously penetrates thin protective layers, creating risks of DNA damage and immune system disorders. Psychological issues caused by extreme isolation and disrupted circadian rhythms are also variables that can reduce mission performance. At present, missions such as Artemis II and the Gateway Station serve as critical research stepping stones. They provide direct measurement data on the effects of deep space on human cells and psychology before humanity officially establishes a long-term presence on the lunar surface. In its early stages, a lunar city is essentially an experiment testing the limits of human endurance, where every cubic meter of pressurized space is calculated to balance operational demands with long-term biological survival. Every design, from transportation systems to habitation areas, must be optimized to extend the survival of the human body within an environment that was never meant to support life. Human survival within pressurized systems cannot be guaranteed if the protective structures consist only of simple inflatable materials transported from Earth. These thin shells are incapable of effectively blocking high-energy cosmic radiation and solar storms, both of which can directly damage the DNA of crew members. In addition, the impact frequency of micrometeorites, combined with extreme temperature fluctuations ranging from above 100 degrees Celsius to below negative 170 degrees Celsius, creates continuous physical stress on materials, easily weakening the structural integrity of mechanical joints and environmental control systems. To overcome these limitations, a lunar city must transition from a model of temporary modular assemblies to a closed fortress-like structure with thick protective layers. The most practical engineering solution is to cover habitation modules with a thick layer of regolith or construct multi-layered structures that take advantage of the moon's natural soil for thermal insulation and radiation shielding. Burying part of the base underground helps maintain more stable temperatures and minimizes the risk of direct impacts from particles traveling through space. One major strategic research direction today is the use of lava tubes as natural shelters formed by ancient geological activity. Topographical analysis models indicate that these structures are large enough to contain the entire infrastructure of a city, providing a thick rocky shell that serves as a natural protective barrier against all harmful effects from the surface environment. The operation of protective structures and pressurized systems depends entirely on the ability to provide a continuous and stable energy supply. While solar panels are the most common power solution in space, they face a major physical limitation. The lunar night cycle lasts nearly 14 Earth days. Storing enough energy to sustain operations throughout such a long night cycle using chemical battery systems would create an enormous burden in terms of transport mass and logistical costs. The engineering contradiction lies in the strategic objective itself. The regions richest in water ice are located deep within permanently shadowed areas, where solar energy cannot reach. This makes nuclear energy an unavoidable choice for an extraterrestrial city. NASA is currently focusing on the development of the Fission Surface Power System, featuring compact reactors designed for autonomous operation and capable of providing a stable power supply regardless of lighting conditions. Organizations such as Rolls-Royce are also developing microreactor designs capable of being deployed flexibly across the lunar surface. Alongside surface infrastructure, agencies such as DARPA and NASA are advancing nuclear thermal propulsion technology. This mechanism uses a nuclear reactor to heat propellant, generating significantly higher propulsion efficiency than chemical engines, thereby reducing travel time for space missions. The stability of compact fission reactors is the determining variable in whether a lunar city can maintain continuous operation indefinitely. Mastering space-based nuclear energy is an essential engineering foundation for humanity to begin expanding its presence to other planets within the solar system. The establishment of nuclear power systems and the ability to extract water ice on-site have transformed the moon's role from a purely exploratory destination into a shipyard and logistical hub for Mars missions. If spacecraft are launched from the moon's low-gravity well, the energy required is significantly lower than that needed to escape Earth's gravitational pull. Once the process of water electrolysis for producing liquid hydrogen and oxygen operates reliably, the Moon effectively becomes an extraterrestrial refueling station, enabling the optimization of payload capacity and reducing dependence on resupply missions launched from Earth. The Moon serves as a real-world testing environment for infrastructure 3D printing technologies, closed-loop life support systems, and ISRU resource extraction before these systems are deployed on a larger scale on other planets. Building cities on the Moon marks the beginning of humanity's transition away from absolute dependence on Earth's resources and physical limitations. Every advancement narrows the distance between humanity and Mars. In your opinion, what is the most difficult technical barrier to overcome for long-term settlement? Leave your thoughts in the comments below, and don't forget to subscribe to follow future videos. Goodbye, and see you next time.